So now, what do you mean by a counter? A counter is the another class of registers, or is another example of a register. Okay. Now, when I call a register as a counter, if entity, a counter is again a register, right? It is a register. A register or additional entity which gives me a specified pattern of output. A register which gives a specific pattern of output is called as a counter. Okay. So as it is giving a specific pattern of output, okay, so it may be a specific pattern of output or it may be a sequence of output. So it may be a continuous sequence of output, whatever it may be. Okay. So that's why this is also called as what? Pattern generator. So if anyone asks you to design a pattern generator, don't scratch your head or don't say that it was not done. Okay. Counters and pattern generators are interchangeable. Why I call it a pattern generator? It is a register which is giving me an output in a specific pattern. What do you mean by a specific pattern? If I say, okay, I want my output, say it's a 3-bit counter, which can say it's a 3-bit register. Okay. Now I want the output of this register at clock 1. I want my output to be like 001. Okay, in the next clock pulse, I want my output to be 110. The next clock pulse, I want my output to be 011. So something like this. In a specific pattern, if I'm getting an output, then I call it as a counter. Fine. So that is a class of a register. Now, this counter, I said that it will be giving me an output patterns, right? So now whatever output I'm going to take from this register, it's just a group of entity, right? I mean a group of flip-flops. If I say I have a 3-bit register, what do you mean by that? I'm having 3 flip-flops with it. And if that flip-flop is generating me output something like this. In the first clock pulse, I'll be getting my output as 001. In the second clock pulse, I'll be getting my output as 110. In the third clock pulse, I'll be getting my output as 101. So something like this. So I'm getting my output in a specific pattern. So that's why I call it as a pattern generator also. Now, each specific output, whatever I am getting now, I call this as a state. We have used this term state in many places, right? So, what is state in a counter? A specific pattern of output, whatever I am getting now, I call it as a state. And the multiple outputs, whatever I am getting like this, so this is called as a sequence. This is called as a sequence of output, right? So, if a counter is having m states, m distinct states, then I call it as an m modulus counter. Okay, so what is this? This is a counting sequence. Each specific output is called as a state, and multiple such states in every clock pulse, it will be keep on changing, no? So I call it as a counting sequence. And the states, whatever I'll be getting, how many such states are there? Depending upon that, I'll say it is that many mod counter. So modulus counter. I call it as a modulus counter. So what do you mean by that? If I'm having m mod counter, what do you mean by m mod counter? It is having m distinct states. That's the meaning of it. It is having m distinct states. That is the meaning of it. M distinct states are there. Then I call it as a m mod counter. Okay. So, what's the counting sequence? The order in which I am getting my states is called as a counting sequence. Each specific output pattern is called as a state. The order in which the states are coming is called as a counting sequence. And how many distinct states are there? Based on that, I will be telling it as a that many mod counter. Is this clear? Now, the states, whatever I'm having, no, I can represent it in a form of a graph. Okay, so the graphical representation of this. So the graphical representation of the states, whatever I'm having, I call it as a state diagram. Remember these terms. We'll be very often using these terms. What do you mean by a state diagram? A graphical representation of a counting sequence is called as a state diagram. Okay. For example, if I'm having three sequences over here, how it is going? The first sequence is 0, 0, 1. The second sequence is 1, 0, 0. So from here I'm going to this sequence. From here I'm moving to this sequence. No. Now how do I represent it? So I'll say it may be like this. 0, 0, 1 is my first sequence. I put one round to this. Then from here where I'm going to the next sequence, which is 1, 1, 0. So this is where this comes. Then from here where I'm going to the next sequence, which is 1, 0, 1. From 1, 0, 1, it will be actually always like this. From 1, 0, 1 again it goes back. It will be what? Okay, so this is how the sequence goes. So now this graphical representation, what am I having? What I call this? I call this as a state diagram. Is this is clear? What is a counter? A counter is one more example of a register. It's a type of a register. Now, when I call a register as a counter, if it is giving me a specific pattern of output or a specific pattern of sequence of outputs, then I call it as a counter. Then that each specific output, whatever I'm having, I call it as a state. And if I'm having multiple number of states, the order in which the states comes, then I call them as a counting sequence. And how many states I'm having with each register, each counter. So based on that, I call it as an M modulus counter. If I'm having M distinct states, then I call it as an M modulus counter. Then how do I represent graphically the output pattern, whatever I'm having, I'm going to represent it graphically, right? And that graphical representation, I call it as a state diagram. Correct? Now, if the states here, in this case, I have made my states to have a binary values, right? So my output sequence is a binary value. So I call this as a binary counter. Similar to that, I can have decimal counters, BCD counters. So many counters are available. It depends upon what's the type of format of my output. As my output is in a binary form here, I call it as a binary counters. Okay. So now this type of binary counters, what I'm having, even I call it as a binary ripple counter. Why do I call it as a binary ripple counter? Because the output of one sequence, the happening of one event is connecting to the next event. No? So even I call it as a ripple counter. That's the one way of telling it. If you look at the circuit, then you will understand what exactly a meaning of a binary ripple counter. Okay. So now let us look into how to go for a counter. See, till now we were talking about the shift registers, which are used basically for holding the data or moving the data, right? So in that case, the types of flip-flops, whatever I have used was a D flip-flop. Now, whenever we use a registers as a form of a counter, the one significant change you have is instead of a D register, here in the counters, usually you will be making use of a T registers. Toggle register. Why? Because that helps me giving me a specific pattern of output. Okay, so now let us take a example of one binary ripple counter. So let me design a 3-bit ripple counter. Okay, so what I have done, I need to take 3 flip-flops, correct? Now what's the type of flip-flop I'm taking? I'm taking a T flip-flop. This is my T. I'll give a clock which is given to all the flip-flops. This is what I'll be having. Now, what exactly I'm doing here? I want to count the sequence. I have a 3-bit fix, right? To start with, I am in this state, 0, 0, 0 state. Okay. Now, what is this output? Let me call this. These are the 3 outputs I am having. Okay. So let me call them as Q0, Q1, and Q2. So this is my Q0, Q1, and Q2. Okay, so to start with, I'm considering Q0, right? I'm applying the input 0 to T, or okay, let me apply so 1 to T. What is this? Whatever I'll be having over here, no? So this is nothing but my enable. So let me connect and count enable here. Okay, so if it is enabled, my timer T will be 1. If it is disabled, then it becomes 0. To start with, let us assume that I am having all my outputs as zeros. Okay, so now I have enabled the T flip-flop. When my T is equal to 1, then what happens? It will be in a toggle state, no? So in the next, when I apply the next clock pulse, what will be the output of Q0? To start with, when in the first clock pulse, initially, my output was 0. Okay, now I am applying the second clock pulse. When I'm making my T input is equal to 0, I'm applying the clock pulse again. So when I apply the clock pulse, what happens to the Q0? Q0 will become 1, right? Because it is toggle flip-flop. So Q0 has become 1. Now what I'll be doing for the second flip-flop? How I'll give the input to the T of the second flip-flop? So what I'll do now is, whatever the 1 minute. Now let me give an enable to all the flip-flops. Okay. Now, during this is a edge trigger flip flop, right? So during the positive edge, what happened? I applied the clock pulse. My T was 0. I have applied the clocking. So during the positive edge, it was 0. So this has become 1 now. When I apply the next clock pulse, now sorry, clock pulse I have to change. Clock pulse, this is my first clock pulse. I have applied for these things, I have not yet given a clock pulse. So when I apply the first clock pulse, from 0 it changed to 1. Okay, this is a positive edge. Now what I do, whatever output I am getting here, that is Q bar, this I give it as a clock pulse to the second flip flop. See, this I am giving as a clock pulse to the second flip flop. So now what happens? When my input has become 1 here, that is Q becomes 1, Q bar will be 0, right? So 0 is applied over here. So when I apply 0, that is, it is going down. My clock pulse is going down. So as it is going down, then what happens here? There will be no change in the output. Correct? So it was 1. To start with, all of them are 0. Then it changed to 1 because of the application of a clock pulse. When I apply a clock pulse, it was a positive edge, so it changed to 1. But what is happening to this? This is a clock pulse I am applying, right? So now, whatever output I am getting at my first flip-flop, that is acting as a clock to the next flip-flop. And that too, which output? That's the not a normal output. It's a complementary output is given as a clock pulse. So when this becomes 1, obviously this will be 0. So what does this 0 does? That 0, whatever I am having, no? So that will keep, at that instant, it will keep it as a no change condition. Now again I apply the clock pulse. When I again apply the clock pulse, what happens? This bit becomes 0, right? When this bit becomes 0, then what happens to this bit? This is 1. So 1 is nothing but a positive triggering for this. So what happens during this positive triggering? My T is 1. So whatever output I had, it was 0. So that output changes to 1. So this becomes 0 and this bit becomes 1. Right? and this bit will be 0. Now what is happening? This is given as an input clock pulse to this. Correct? So this has given us a clock pulse to this. During the next clock pulse, what happens now? So this was 0, this is 1, this is 1. So as this was 0, when I apply the next clock pulse, this becomes 1. What will happen to this? As this becomes 1, this will be 0. So this is in a no change condition. And as this is 1, this will also be 0. So this will be the no change condition. See, I got it as 0, 1, 1. Now let us apply the next clock pulse. So when I apply the next clock pulse, this 1 becomes 0. So when this becomes 0, its complementary output will become 1. That is given as a figure into this. So this becomes 0. When this output becomes 0, what happens to this? This will be a negative. So this will be 1. So as this is 1, then what happens to the output of this? This will become 1. So it is 1, 0, 0. So this goes on like this. So this counter is called binary ripple counter. We have another name for this also. We'll see that in our next class. So if you keep on doing this, you can beautifully see you will be getting a sequence from 0, 0, 0 to 0, 1, 1, 1. That is 0 to 7 count you are going to get by using a T flip-flop as a binary ripple counter. Is this clear? Any doubts?